Hello, everybody. My name is Sathyakumar. I'm from Dr. Ranu Jung's lab, and the title of my talk is Multidimensional Mapping of Stimulation Parameter-Elicited Percept Intensity Space for the Development of an Automated Fitting System. Okay. Now, it's a long title. So what I want to do is just break it down into three concepts that I hope you'll take away from my talk. First one is I'll start off by explaining what I mean by multidimensional mapping. Second, I'll talk about what I mean by fitting and list why I think we need to automate it. And third, I'll talk about the term stimulation parameter elicited percept intensity space, which henceforth I'll refer to as stim percept function, and basically describe what methods we're using to characterize the stim percept function. Now, before I start off, just a quick background on what electrical neurostimulation device is. In short, electrical neurostimulation device is a device that uses electric current pulses to alter neural activity. So now you can alter neural activity either by adjusting the amplitude of the current pulses that you deliver, or the duration of the pulses, or the timing and repetition between the pulses. So in short, the neural activity can be modulated by multi-dimensional modulation of current pulses. Now, which of these dimensions do you use to modulate the neural activity will depend on the type of interface that you have, the target neural tissue, and your application. Now, there are three well-known examples of neurostimulation devices that have made an impact on healthcare. One is cochlear implants, which have been used to restore hearing, spinal cord stimulator devices, which are used to treat chronic back pain, and deep brain stimulation devices, which are used to treat Parkinson's and epilepsy. Now, in our lab, we have developed a new neurostimulation device to provide sensory feedback to individuals with upper limb amputation. Now, there are three main components to this device. One is you have a prosthetic hand with embedded sensors in it. And then second, you have a stimulation processor. And third, you have a wireless implant with electrodes implanted inside the fascicles of the nerves in the upper arm. And the simple explanation to how this device works is signals from sensors on the prosthesis are mapped to stimulation parameters on one or more electrodes that are implanted within the fascicle to elicit task-relevant sensation. Now, to understand a little bit deeper into what is involved in going from a sensor signal to a desired percept, let's look at what are the blocks in the signal chain. Now, you have two main blocks. One is you have the sensor stim mapping block, which basically is the task performed by the stimulation processor, and it takes a sensor signal and converts it into stimulation parameters. And then you have a stim percept space, what I call the stim percept function, which defines how these stimulation parameters affect perceived intensity. Now, the stim percept function is dictated by the physiology and the electrical interface that you're using to connect with the neural tissue, while the sensor stim mapping is completely in control of the user because it's programmable processor outside. Now, in a simple case, when you have one sensor on the prosthesis, such as a force sensor, that is mapped to one stimulation parameter on one electrode, if the stim percept function is a linear function, then a linear sensor stim mapping function should be sufficient to elicit the desired percept intensity for a given force signal. On the other hand, if you have a step sigmoid, if your stim percept function is a step sigmoid, then a linear function might not be optimal. You may need a nonlinear function for the sensor stim mapping to elicit the desired percept. So what the key message from the last two slides is that you need to understand the stim percept function for that particular electrode in order to set up an appropriate stimulation map for that electrode. Now, in addition to that, what I described to you was a very simple case in which you had one electrode mapped to one sensor mapped one electrode modulating one parameter. But in reality, what you have to get a level of function equivalent to a biological hand is you have a prosthetic hand with multiple sensors, at least 10 sensors. and you have an electrode interface with the nervous tissue, which has many more electrodes, and information from these sensor signals need to be mapped to multiple electrodes, and on each of those electrodes you can modulate the stimulation signals along multiple dimensions of the current pulses, along the amplitude, pulse frequency, or pulse width, and you do all of this to modulate the elicited percept intensity along multiple axes in terms of what is the quality of sensation that you receive, whether it is touch, pressure, or stretch, and what is the intensity of percept, and where do you feel it in your hand. Now, if we were to use a manual method to determine the appropriate sensor stimulation mapping for this, it's likely going to be suboptimal because of the complexity of the mapping involved. It's going to be time consuming, and it's also frustrating to the user. And all of these three factors make it difficult for clinical translation of this device. And hence, I believe it's needed, there is a need for an automated system to perform this mapping to enable clinical translation. Now, how is the fitting done right now? There are a few groups who are working on this topic, and in our lab, the way we do the fitting is we fix the pulse amplitude and the pulse width, and modulate pulse frequency based on the sensor signal on the prosthesis to provide feedback. In another group, the way they do it is they keep the pulse amplitude fixed and modulate pulse width and pulse frequency in a linear manner to elicit the desired percept intensity. So what you're seeing is either you're modulating one parameter or at most two parameters to elicit the desired percept. So the focus of my doctoral work is basically to see if we can improve on the current fitting methods. And I've approached this problem by dividing it into two parts. First, I want to develop methods to characterize the stim percept function after electrode implantation. And second, I want to develop methods to use that stim percept function to configure this sensor stem map in an automated manner. So in this talk, I'll mostly focus on the first goal, which is characterizing the stim percept function. So how would we go about characterizing the stim percept function? To map the stim percept space, we extended the method of finding strength duration curves to determine points of equal subjective intensity in the stim percept space. So let me walk you through an example of how we actually do it. So to find points on a strength duration curve, which is a topic that many of you may be familiar with. So to find the strength duration curve for threshold, also known as a point where stimulation is just perceivable, you can take one point where you fix the pulse width and you ask the subject to adjust the amplitude of the stimulus till they reach a point where they just start to feel the stimulation. And if you do that for multiple pulse width values, then you should get a plot that you should get points on a plot that looks something like the one on the left. Now, you can take that point and then apply a Weiss transformation to transform it to a charge duration plot where it's going to be a linear function of charge. The charge is going to be a linear function of pulse width. You can apply a linear fit and then transform it back to get a strength duration curve. And the strength duration curve, which you see on the left in violet, essentially represents all points where the stimulation is just perceivable. And this is what I mean by an isopercept intensity curve. Now, you can apply the same method to find the isopercept curve for maximum comfort level. And one thing I forgot to mention is you can find these points either using a single stimulus pulse or a burst of pulses. And in the experiment that I'm going to describe later on, we use the burst of pulses so that we also can look at how pulse frequency in that burst affects the location of the isopercept curve. Now, in order to find the intermediate intensity curve, what we use is a burst pair where we have a reference stimulus and the subject is asked to adjust the amplitude of the test stimulus so that both the intensity elicited by both the burst pairs feel the same way. So what you see on the plot below is the reference stimulus marked by the star, and every point along this green curve is a point that feels the same as the percept intensity elicited by the star. So this way you can sample the stim percept space after the electrode is implanted. And using the same method, you can also test how these isopercept curves vary along the pulse frequency axis. So if you have a test burst, which is a different frequency than the reference burst, then you ask the same question and say, okay, find the amplitude point where the test burst feels the same as the reference burst. So now, in order to develop these methods further, you can either test it in implanted subjects or in able-bodied subjects. Now, there are obvious challenges to collecting data from amputee participants with implants. So an alternate stimulation platform that can be used with able-bodied volunteers was used to develop the methods to map the stim percept space. This is a technique that was developed by Dr. Andres Pena in our lab. And the basic idea here is you use channel hopping strategies to activate the nerve without eliciting any cutaneous percept under the electrode. Now, what this method really means for me is two things. One, it lets us work with able-bodied subjects to develop and refine the methods. And two, by using the channel hopping strategy, you can deliver extended periods of stimulation without causing discomfort under the electrode. So this is a picture of the setup on the right. You basically have hydrogel electrodes were placed at the wrist on an able-bodied participant seated at the table. After each stimulation pulse is delivered, participants use buttons in front of them to adjust the stimulation amplitude or indicate their response. And so far, data has been collected from 7 able-bodied participants. Isopercept curves were mapped at 4 different pulse widths, 100, 200, 400, and 700 microseconds, and 2 pulse frequencies and 3 repetitions of pulse amplitudes were found for each pulse width pulse frequency combination. And the reference for the intermediate levels were chosen at 50 or 80% of the difference between the comfort and the threshold at 700 microseconds. So the point indicated by the star. Before I present the results, just a disclaimer, I'm in the process of still analyzing my data. So what the results I'm showing are preliminary results from individual subjects without any aggregation. So the first one is saying, okay, can you get distinct isopercept intensity curves? And this is data from one subject showing the individual data points and the vice fit where you get distinct strength duration curves. The next thing we looked at was, does pulse width affect the separation between the curves? And in order to find that out, I basically plotted the plot on the left where you have the difference between each of the threshold and 2 intermediate levels with respect to the threshold curve at different pulse widths. And what you see is that the gap between the curves is different for different pulse widths, indicating that pulse width makes a difference in moving between intensity levels. And finally, this is an aggregated data where I was looking at whether if you use a different pulse frequency, will that cause a shift in your isopercept intensity curve? And the way I'm measuring that is basically looking at the difference between the amplitude values reported at a lower frequency subtracted from the amplitude values reported at a higher frequency, and what one would expect based on the current understanding of how percept intensity is actually translated physiologically is that at a lower frequency, you would need a higher amplitude to elicit the same percept intensity level. So which means if you subtract the amplitude between lower and higher, you should get a positive value, which is what you see in this plot. So to summarize, basically what I've talked in the mice what I presented so far is what is multidimensional mapping, what I mean by that, and why is it needed. So it's basically modulating the stimulation parameters along multiple dimensions to elicit the desired percept. I've talked a little bit about what is a fitting system and why is there a need to automate it. You have multiple sensors need to be mapped to multiple parameters and multiple electrodes. Doing this manually is not going to be easy, and there's a need to automate it. And lastly, I presented a way in which we are characterizing the stim percept space using a modified strength duration curve determination method. Thank you.